In this lesson, we learn a method called maximum likelihood estimation. This is a very popular statistical method, and the estimate out of this method enjoys very good property. We will talk about the properties after we learn what is this method, how to derive an estimate based on this method. This method was actually introduced by R.A. Fisher in the 1920s, even though it was a long time ago, but it's still very popular and very powerful, and even has a good efficiency in the sense that the estimator obtained with this method has approximately minimum variance and is also approximately unbiased. We'll illustrate with an example. For this example, we consider email account, whether a password is strong or not strong. Suppose that the individual's password, out of many people's password, 25% of individuals' password are strong. So 25% are strong passwords, and the remaining 75% are not strong password. So this is just an estimate, but we suppose for a population, we do not really know what is this proportion of passwords that are strong. Instead, because in order to know that, we really need to know exactly what is the password and whether the password is strong or not. So we do not really have the information. Instead, suppose we have a sample. The sample contains 10 individuals. Out of these 10 individuals, we have 3 of them whose passwords are strong. Suppose X1 is the first person's password, and X1 is indicator of whether the first person's password is strong or not, has strong protection or not. And X2 is whether the second person's password has strong protection or not, and so on. So we have X1 through X10, and suppose that in the observed sample, we have X1, X3, and X10 being 1, and the rest of them are 0. So for this case, what we observed are discrete data, these binary discrete data, and they are all independent. And for this case, if we consider the probability distribution of these 10 persons' password, whether they are strong or not, we will have the computation like this. Say the first person's password is strong, so we have a probability of X1 equals 1. And the second person's password is not strong. So here, probability of observing, so what we have is X1 equals 1, and X2 equals 0, X3 equals 1, and so on. X10 is equal to 1, and the rest of them is 0 for all other i's. Okay, so those are the observed data. And what is the probability of observing the xi equals the little xi, and that's for all of them. And this for all of them is really referring to that we are considering the 10 persons in the sample. So here is I equals 1 up to 10. And these 10 individuals are independent of each other. And we learned that if they are independent, then the probability of these intersections becomes the product of individual probabilities. So the probability of X1 equals X1, and the probability of the X2 equals X2, and up to the X10 is equal to the observed X10. So these capital letters are the random variables for any randomly selected subjects, whether their password has strong protection or not. And the lowercase letter refers to the observed value being 1 or 0. So X1 being 1, that gives us the probability being the P. Suppose P is proportion of those that are strong, have strong protection. x2 is a 0, and the probability of 0 is 1 minus p, and so on. So out of these 10, we have 3 of them having strong protections. So we really have a p to the power of 3. Okay, I'm sorry, I shouldn't. This is just for this particular example. If we have 3 of them, I would have p to the power of 3 and 1 minus p to the power of the 10 minus 3, because there are a total of 10. So 1 minus p times 10 to the power of 10 minus 3. So that's for this particular sample. And for this particular sample, we observed such data. The maximum likelihood method basically is trying to think that what value of p could have made this probability highest such that the data is observed. So we already know that this probability is p to the power of 3 times 1 minus p to the power of the 7. And we ask the question of what value of p makes this probability highest. That's make us observe the x1 through x10. And so the maximum likelihood method is basically trying to consider this probability, and we call that probability as a likelihood function. Try to make this likelihood to be as big as possible. So if we think about this function p to the power of 3, 1 minus p to the power of 3, this is really a function of p. And if we plot it, this one, I'm going to denote this function as the likelihood of p, L of p, okay? For this likelihood of p, when we plot it, this is how the picture looks like. When the p, the p is the proportion of passwords that have strong protections. So p is between 0 to 1. And if p is 0, we try to look at what is the value of this function. So p is 0 is basically close to 0. And if p is 0.05, and it has a probability. And if p is 0.1, it's another value, and so on. So as we increase the value of p, we see that this picture shows that the probability increases first, and then at some point, it becomes the highest and then starts to reduce. So that's how this probability of observing the 3 strong passwords and 7 of the weak passwords, how that changes with the p. So out of this plot, you can see what value of p that maximize this probability that's somewhere around here. So we basically need to find the value here. What is it in the p that makes this function maximized? Quite often, for the calculation, it might be easier to instead of directly trying to maximize a function, this function generally involves such power, such as the p to the power of 3 and 1 minus p to the power of the 7. Because when we have data observed, quite often involves random samples, and therefore they are independent. So we see this kind of power quite often. To work with power and try to maximize it is not as easy. Instead, it would be much easier if we take the log transform. So for this one, if we take the log transform, the log of the natural log with base e, okay, log of this one is 3 times the log of p, and then plus 7 times the log of 1 minus p. Once we convert it after the log transform, this function would be much easier to try to maximize. The function itself, in picture, it may not look as beautiful, but this one is the log of the function. So for this log of function, still the maximum happens around the similar place as the original probability. But this function, if we try to work with it, it's easier to try to maximize that. Okay, so this is the log of that. So basically, here is what I would just explained. The log of the probability distribution or probability density function for the data that we have observed. the left-hand side here, this is the joint density function, joint probability distribution function from the data, and then we take the log. This joint probability function is a function of the data and also a function of these unknown parameters. For this example, there's only one unknown parameter p, and x is the observed data. We no longer treat this function as a x variable. Instead, treat the p as the input variable. So it's a function of p. When it's treated as a function of p here, we maximize it. Because it's a convex function, we can just take a derivative and set it, take a derivative with respect to p, and then set it equal to 0 and solve for the p. Okay, so for this case, when we take the derivative for log p, we get 1 over p. For the log of 1 minus p, we take the derivative, we will have 1 minus p inverse, -1. As you see, because we don't have the power here, instead it's the two terms sum up, the derivative is just the sum of the two derivatives. If we worked with the original one, p to the power of 3, 1 minus p to the power of the 7, if we try to take derivative, that one we will end up having to use the chain rule. And the chain rule would be a lot more complicated, need the chain rule. It's a lot more complicated to compute that than if we have done, I mean, for that chain rule, that's very messy. Okay, so working with the log transformed of this likelihood function make it a lot easier. So after we try to set this equal to 0, so make this thing equal to 0, and then solve for the p. So in this case, it becomes like 3 over p equals 7 over the 1 minus p. So we can cross multiply. So 7p is equal to 3 times 1 minus p. And you solve for that, you get p equals the 3 over 10. Okay. So that gives us p is 3 over 10. It gives the likelihood estimate. And this kind that we obtained by maximizing the log likelihood function is called the maximum likelihood estimate. And for this maximum likelihood estimate, what we obtained is the value of the parameter such that it made the likelihood maximized. Likelihood of observing the data maximized. So for this particular example, if we actually try to write the exact distribution of observing 3 of the strong passwords out of the 10, rather than knowing specifically x3, x10 give us strong password, in that case, the probability for that would be using the binomial distribution, is the 10 choose x and times p to the power of x and 1 minus p to the power of 10 minus x. This is the binomial distribution of observing x passwords that have strong protections, and we have x being 3. So we put in x being 3, that's the observed value. Now this is the probability mass function as a function of the parameter p. And then we maximize it by taking the log and then take derivative, set derivative equal to 0 to solve for the p. So let's now introduce the formal definition of maximum likelihood estimate. So we have observed in a simple random sample, x1, x2 up to xn. That's a simple random sample. And for this simple random sample, we have the data observed, and these data are recorded as little x1, x2, and so on. So these are the observed sample. Little x1, x2, and so on. This is the simple random sample. And from the simple random sample, we try to get the joint probability distribution of them. And this joint probability distribution most likely is going to be the product, okay, of each one of them. So f of x1 of x1 and f of x2 of x2. And up to the last one, xn and xn. So these are the probability density function of each one of them, and we multiply it together because what we have is a simple random sample. And for simple random samples, they are all independent. So this is the joint probability density function. So that's this one, okay? And for this one, we try to maximize it because it has the unknown parameters theta in there. The theta, depending on the distribution, there might be multiple parameters. For example, in the normal distribution, you have the mu and the sigma in there, so 2 parameters. And the parameter values that maximize this joint probability distribution is called maximum likelihood estimate. So here the theta such that it makes this probability to be function to be maximized. Those are the MLE. And this function itself, when treated as a function of those unknown parameter thetas, this function is referred as the likelihood function. The maximum likelihood estimate would give the parameter values whose observed sample becomes the most likely, that has highest probability. So basically what we need is to compute this probability of observing that sample. So basically if we have a continuous variables, we'll compute the joint probability distribution. Here's an example. For this example, we have a sample from exponential distribution with parameter lambda. Exponential distribution has a density function given by this one and has a one parameter. That parameter is the lambda, which is the rate. So here, f of x with the lambda is lambda e to the negative lambda x for x greater than 0, and it's 0 for otherwise. So this is the probability density function for each of the observation. And what we have here is a random sample, which means x1, x2 up to xn, they are independent. And what we want to estimate is the lambda. First, let's write down the likelihood function. Likelihood function is the probability, joint probability distribution of all of them. So this one is the f of x1, the first observation's probability density, and so on. This one is the last observation's probability density. They are multiplied together because they are independent. And then we simplify it. All the lambdas put together is lambda to the power of n, and then the power on the exponential will combine them together. That becomes negative lambda summation of xi. And here, for this PDF, again, because of the power, if we directly try to maximize it to find the lambda, is inconvenient. So it's better to take the log transform. So when we do the log transform, it becomes n times log n and lambda minus lambda summation of xi. For this function, this is a function of the lambda. We can denote this one as L of lambda. So this is going to be a likelihood function treated as a function of the lambda. And then we take the derivative partial L with respect to the lambda and make it equal to 0 to solve for the lambda. So for this case, when we take derivative, the first term will give us n over lambda. Second term will give us the summation. So we set it equal to 0, we will get this n over lambda minus the summation being 0. Therefore, our lambda is going to be 1 over x bar. So the maximum likelihood estimate called MLE. Okay, MLE is simply just 1 over x bar. And if you could recall from the previous lesson, the moment estimate is also 1 over x bar. So the two are identical. This next example is normal distribution. When we have a simple random sample from normal distribution with mean mu variance sigma squared. So in this case, there are two unknown parameters, the mu and the sigma. And we also want to derive the maximum likelihood of these parameters. So first, write down the joint likelihood function. So this is the joint likelihood. That's the distribution PDF of the first variable, so x1 of x1, and so on. This one is the last one, the xnth PDF. And for the normal, is this e to the power of half of squared standardized value. Okay, and then we combine the terms like square root of 2 pi sigma squared, all n terms have that term. So we have this to the power of n. Because we can take square root out, so it's half to the power of half of n. And then in the power, exponential power, we combine them, we get e to the power of negative summation term there. And then because of still a lot of the power there, it's convenient to first take a log transform, and then we try to find the maximum of it. The log itself, why we always do the log transform? If you have any of the function, okay, so let's say you have g of x, and you consider the, I'm sorry, instead of g of x, I'm going to just write it as g of theta, because we've been using theta as the parameter. The log transform of that, the log of it, log g theta. The log function behaves like this when g theta x1 is 0. So it's like this one. Here is the g theta being 1. This is the d theta, and here's the 1. Okay, so the log transform, because the log is a monotone increasing function of the whatever before the log transform. So if the value achieves maximum at somewhere on g theta, then this log g theta achieves the maximum at the same place. That's why we're doing the log transform. And log will convert all the product to the summation. That's the helpful part of using the log transform. So back to this one. So what we have is the log of the likelihood. This log likelihood, again, we treat it as a function of just the parameter mu and the sigma squared. That's this one. And then you can take the partial derivative with respect to the mu and set it equal to 0. And also the partial derivative with respect to the sigma squared. Treat the entire sigma squared as one term and then set it equal to 0. When we do this, we will get the maximum likelihood estimate. In particular, like the first one, when we take this partial derivative with respect to the mu, it will disappear. So only the second term will be there. From the second term, when we take partial derivative, we get this twice of the summation, and we are going to have mu minus the xi, and make this equal to 0. So that's from the first equation. When this equal to 0, you will see the mu is going to be the average of the xi. Okay. Once we have the estimate of the mu, and then we put into the other one, we can solve for the sigma squared. After finishing solving the equation, what you get is that for MLE, estimate of mu is the average, sample average, and the MLE of the variance is this average squared deviation. This time it's n in the denominator rather than n minus 1. So that's the result of solving for the MLE from the normal distribution. If you see the distribution is normal from now on, you no longer need to derive just like I did in the exercise. Instead, you can directly use these two, the formula here, and use it directly to find the MLE estimate. Okay, so next one is talking about estimating the function of parameters. The MLE has a very nice property. This property is if you have a MLE obtained for parameter theta 1, theta 2, and so on, and you have also a function of these parameters, then the MLE of the function does not need to be obtained through other distributions. Instead, you can directly plug in the MLE in the function. So if thetas have a MLE given by theta hat, then the h of thetas will be estimated by the h of theta 1 hat, theta 2 hat, and so on. This one is also MLE. We say it's an MLE that has some very important property that will come up next. Okay, before we move on, talking about property, here is an example. We know the mean and the variance. Their MLE is simply the average, sample average, and sample squared deviation. If we want the MLE of the sigma, because the sigma is a function of sigma squared by taking square root, then the MLE of sigma is simply the square root of this average squared deviation. So this is the MLE of the sigma. Of course, this one is different from the sample standard deviation. In the sample standard deviation, we have n-1 there. This one is good for the large n. If it's smaller for small n, the 1 over n is biased. Okay, so what are the good properties of the MLE? When the sample size is large, we have some very good property for the MLE. One of them is that if the sample size is large and the maximum likelihood of the parameter would be approximately unbiased. So here, if you have MLE computed for theta, and this MLE is theta hat, then in the long run, the theta hat is going to be centered at the theta. And beyond that, we also theoretically know that this MLE estimate theta hat will have the variance close to the smallest. Close to the smallest is because smallest out of all the unbiased estimators. So-called closest to the smallest because sometimes it's not exactly unbiased, it's close to the unbiased situation. If n is large, then it's approximately unbiased. That's why in the end we say that this theta hat is approximately minimum variance unbiased estimate. The next thing that we already mentioned that the other thing is the invariance principle. That principle allows us to easily obtain the MLE of functions of parameters. So I do not need to repeat here. So that basically is all about the maximum likelihood estimate. The MLE has a very nice property, but it does require quite a lot of computation if the model is complicated. So far, we practiced just a few examples, the exponential, the normal, and also the binomial case. If the data, on the other hand, has a complicated model behind of the distribution, including, for example, it might have multiple variables involved, and those entered into the mean function. In that case, the maximum likelihood estimate could involve quite a lot of computations. And sometimes the parameter values that maximize it may not be able to have a closed form formula for the solution. If that's the case, quite often we use numerical methods to try to find the value. Those numerical methods include, for example, the Newton's method or like gradient descent method and so on. So that's the maximum likelihood estimate. To summarize, how do we find the MLE? We start with the joint distribution function. Work with joint distribution function, okay. And then these joint distribution functions are treated as the parameters of unknown zetas. And then take the log of that, we call it the log likelihood. And this log likelihood, we take partial derivative with theta I and set it equal to 0. That's for all of the i's goes to, say if we have k parameters, I'm going to have k such equations and then solve for these unknown parameters, theta 1 up to theta k, and that will give us the MLE. And MLE has invariance principle and also is approximately minimum variance unbiased estimator. So that's all about this chapter.